Good morning, John. Don't really feel up to the moment, generally. I don't think anybody's a huge fan of moments where it feels like suddenly everything's possible and that there aren't any good answers and there's no way to sort of access what the future will be like, or even how we got here. So instead, today, I want to talk about life on Mars. And I'm just going to go off the dome here, if you don't mind, though I do have some notes. And I just like, it's possible that with the whole world being what it is right now, you did not hear about this, but NASA announced, and there was a paper out, that after a full year of work, Perseverance, the rover, has detected some things on the surface of Mars that we do not know how to explain without there having been life on Mars. Now that's very different from saying that there was definitely life on Mars, and very, very different from saying there is currently life on Mars. But to put this all in context and to talk about like how science works, I'm going to give you the past, present, and future of life on Mars, including this recent discovery, which I think could be quite a big deal. The first spacecraft we ever sent to the surface of Mars was in the 1970s, and it carried a little biology lab. So Viking 1 and 2 weren't just there taking pictures, though the pictures were important because, like, look, they did not know if they might see, like, lichen. They knew that Mars was pretty barren. They knew that the atmosphere was very thin. But there was plenty of talk back then about whether the pictures would show life. And there were definitely biology experiments on the Viking landers that were designed to detect life. So this was, from the beginning, taken very seriously. I mean, even before we were on Mars, there was lots of talk about whether there would be little green men. They were not looking for signs of past life. They were looking for currently existing life. They grabbed a little bit of soil and they put like water and nutrients on it to see if metabolism would start. And the first signal from that experiment was that gas was being released. And that was a big moment. But the way that science works, then you do other experiments to see if maybe that could have been done through some normal kind of chemistry, because like situations on the surface of Mars aren't going to be like situations on the surface of Earth. Other experiments on the surface of Mars showed no organic molecules. And then also we showed that the metabolism could be explained just by weird chemistry rather than by life. There could easily be just reactive compounds in the soil that would mimic the signs of life. So the verdict shifted from maybe yes to probably not. Viking was set up kind of with like one big experiment to decide everything, and that's just so rarely how science works. Now, if they had just taken pictures of some moss, that would have been it. Like, it could have played out that way. But usually it's more like you get a lot of drips, you interrogate those drips, you try and like deal with those interrogations, like a criticism, no, maybe it was done like this. And they're like, okay, we'll check for that. And that's how science works. Measurements, countermeasurements, arguments, contradictions, revisions, science. In 1996, I was 16 years old and I was at summer camp, and another big thing happened. There was this Martian meteorite that was found in Antarctica, ALH 84001. Allen Hills, 84001. And that was a rock from Mars. It had been blasted off the surface of Mars by an impact, and then it had landed in Antarctica, and we grabbed that, and we did science to it, and we looked at it under an electron microscope, and we were like, oh my gosh, this thing looks like a fossil of a bacteria. And that was very big news, and I was very frustrated because I was at camp, and I didn't have my computer, and I couldn't blog about it. So that's where I'm at. Then people were like, look, geology can make bacteria-shaped structures all by itself, and today this is still like in limbo. Like, it is an unresolved, probably forever a maybe sign that there could have been life. And it's like, to me, it's not even a check in either column. Now, to be fair, I skipped over the first part of this story, which is like looking at Mars and seeing, are these canals? Is this like a sign of an ancient dying civilization? And I'm also going to skip some other stuff. Like, Curiosity discovered some organic molecules in some mudstone. When I say organic, that's the chemistry definition of organic, which does not mean made by life. It means part of the large family of carbon-centered chemistry. We've seen weird spikes in methane on the surface of Mars that turned out to be maybe not as weird as we thought. There's also seasonal recurring lines of like dark stripes, which seems like they could kind of be considered flowing water on the surface of Mars. And also a huge amount of planetary science just proving that at one point Mars had a bunch of water running over it. Like, we know that now. We didn't know that when I was a kid. But for the sake of time, we're going to skip up to 2024. Perseverance rover drilled into a rock in Jezero crater, which is part of a dried up river delta that once fed into a Martian lake. This rock looked exciting, if you're the kind of person who can get excited by Martian rocks, which I am. So first thing to know, this rock was formed in a river delta by mud. So there was mud there, and then over time, the water left and the rock was compressed, and now you have what's there now. And the reason this mudstone was particularly exciting is these spots that are all over it. And outside of the spot, you have one colored rock. Inside this spot, you have a different colored rock, and on the edge of the spot, you have a different color to it. So what is happening, definitely, is that something happens in the middle of that, and it changes the rock as it spreads out. And so that on its own is like, that's something you should look at more. And so they did, and Perseverance is a much more complex and capable laboratory than the Viking landers ever could dream of being. And they can look and check specifically what kinds of molecules are in there. And they can see first, there's some organic compounds, which again, doesn't mean life, it means carbon-based. But they also found these two kinds of molecules. So there's vivianite, which is iron phosphate, and there's gregite. I think it's pronounced gregite. It's named after a guy whose last name was Greg, spelled like this. So what this paper is talking about is that in this mudstone, so this like silt and clay that turned into stone, there's iron and sulfur. And in this universe, things that are at a higher energy can release energy and go to the lower energy. It's just like dropping a ball. But these iron and sulfur compounds are like in a stable high energy state. So think of a ball that's like up here, but in a well, so that it's never gonna get out of there unless you like bump it out. Like you gotta shake it up. Iron, its energy level is up here, and it's not going anywhere, right? Even if there's quite a bit of heat, it's not going anywhere. There's no way to get the iron out until there's like a lot of heat, and then the iron goes flying out, and it's not in there anymore, and it falls down. And that can absolutely happen without biology. But you need heat, and heat is the thing that's shaking the cup. It's getting the iron out and then to a lower energy state. And what has happened inside of these spots is that the sulfur and the iron seem to have spontaneously jumped out of the cup. So you have to ask, how did they get out of the cup? How did they get out of their very stable but higher energy configuration to a second stable lower energy spot? They check and they look, and everything else about this environment says this was not a hot place. The chemicals also didn't like form somewhere else and then get deposited there. These chemicals formed where they are. I mean, you can tell that just by looking at it. They're not mixed in. It's like something happened and it spread out. Now, the thing is, when the iron falls out, that creates energy, and that energy can be released in a number of different ways, but it can also be captured by life. So here on Earth, there are microbes that do this. They take compounds that are in high energy but stable states, and they say, okay, well, I'm going to use the chemistry of life to get you out of that state, and then I'm going to use that energy as it falls down to the lower energy state to power my metabolism. And this happens on Earth with both iron and with sulfur, which is what we're seeing here. So like Geobacter is a bacteria on Earth that captures iron reduction to power its metabolism. There are also on Earth sulfate reducing bacteria that capture that happening with sulfur. This is called chemosynthesis. So it's like photosynthesis, where you are like running your metabolism instead of with light, you're running your metabolism with chemistry. And so the question is, did we definitely find these compounds? And it seems like we did. Are there corresponding organic molecules around that could have been part of a living system? And yes, there is. Could it have been super hot and the chemistry have happened that way? And the answer is definitely not. Or could this chemistry have happened some other third way that we don't know about? And the answer to that is maybe. So that, to me, as a person who, knows the basics of biochemistry, is super exciting. Like, that's all right. Okay. We should look into that. But look, again, the chemistry of Mars is different from the chemistry of Earth. We don't know what it was like back then. But if we were on Mars, or if these rocks were on Earth, we could totally figure this out. Like, this would actually not be that hard to figure out whether or not this was done through regular old chemistry or biological chemistry. So now we're going to move on into the near future. What would we do to these specific rocks to figure out if there was life? So life on Earth makes like 4 big macromolecules. You got DNA, you got proteins, you got carbohydrates, and you got lipids. DNA, not probably going to be super helpful when we're talking billions of years ago. It breaks down super fast. Proteins fall apart pretty fast, though there's a chance that some of the individual amino acids would get stuck in amongst the mudstone, and we could find them, but amino acids can be created through non-biological processes, so we would have to find that there was like a preference toward a handedness to those amino acids. So amino acids can be sort of like left-handed or right-handed. You see how like my hands don't line up perfectly, even though they're mirror images of each other. So there could be mirror images of amino acids, and life, you only uses one of those mirror images on Earth. And probably that would be the case everywhere. It wouldn't be the same mirror that would be used. They would either choose left hand or right hand, but they wouldn't do both. And so if there wasn't a 50-50 mix of the handedness of the amino acids, that would be basically a smoking gun. I would say that was life. But over that vast quantity of time, the handedness might actually be lost. So this might not be the smoking gun. Next, lipids, they're tougher. And so we could probably find lipids. This would not quite be a smoking gun. Now, if it was certain like sizes, and this is like cell membrane stuff, then that would be like, whoa, okay, that's a pretty big hint. But lipids can actually stand up for a long time. We have found lipid remnants in rocks 2 billion years old on Earth. But here's the big one. isotopes. So carbon specifically occurs naturally as carbon-12, which has 6 protons and 6 neutrons, but also carbon-13 and other isotopes. And carbon-13 has 6 protons and 7 neutrons. Life prefers lighter isotopes. So if you took all the carbon out of my body, I would be dead, and so I wouldn't be able to talk to you anymore, but you have a pile of carbon. And then if you took all the carbon out of a bunch of pencils, you laid them next to each other, there would be more carbon-13 in the same number of pencil atoms than there would be in my atoms. We know this. We've known this forever. It's an extraordinarily useful quirk of physics. Life prefers the lighter isotopes, and so if you want to figure out if something was living or not, you can look at the carbon ratios and you could determine for sure whether it was alive. So this is probably going to be how we do it, and it's not complicated science. I mean, it's getting the stuff to Earth, very complicated. The science itself, of course, complicated, but not something that's new or that would be difficult to do. And this is the kind of evidence that Earth's earliest life rests on. We do isotopic fractionations of stuff that's frozen into 3.5 billion year old rocks in Australia and South Africa, which are like the oldest rocks on Earth, because Earth, this is going to become important later, is very geologically active, constantly recycling rocks. So we don't have like many of the rocks from the early Earth to work with. Mars, not like that. But to get the samples back from Mars, you have to do the sample return mission. And this Perseverance is designed for this. It can package up samples from Mars. It's been doing this. It leaves them behind, and they're there to get picked up and brought back by a robot, not by a person. And that mission has not launched yet. It's been somewhat fraught in getting it done, in getting it funded. It's a complicated mission. And at the moment, it's a little bit in limbo. Definitely not going to happen in the 2020s. It will hopefully happen in the 2030s, which will be great because I will theoretically still be alive then. But again, this is what science looks like. So we have all these little puzzle pieces. We're getting more and more puzzle pieces all the time, but only when we actually do the science. They don't just come in. We actually have to do hard, clever science. And those clues pile up, and some fall apart under scrutiny. Others are scrutinized and they continue to gain strength as they don't fall apart under scrutiny. If the leopard spots in this rock are really biosignatures, Mars was inhabited by life. But here's the thing, the moment you accept that, you don't get closure, you get new mysteries. For example, did life start independently on Mars, writing its own version of biochemistry as we did ours? And that would, for me, be the most exciting version of this story. That would basically mean life is extraordinarily common in the universe. It wouldn't necessarily mean complex life is common in the universe, but it would mean life is common in the universe. If it happened twice in one solar system on 2 neighboring planets, it happens all the time. And we could probably tell if it did its own version of biochemistry, or in the other direction, if there was one single origin that ended up on 2 different planets, which would also be very interesting and important. So we know that planets are swapping parts through impact ejecta. We know that some things can survive in space for fairly long periods of time. So it might be that life started on Earth and then was transported to Mars, or it might be that life started on Mars and was transported to Earth, or it might be that life started somewhere else and was transported to both places. But which that would be extra wild, and also I don't think there'd be any way to tell the difference between any of those circumstances. But maybe. But also, if there was life on Mars, this opens up something I don't think people talk about that much. The earliest evidence we have of life on Earth is about 3.5 billion years old, but that's not because it probably was the oldest life, just because that's the oldest rocks we have. If there's a definite biosignature on Mars, that would, one, prove that we are not the only planet with life on it, but it might also give us access to the earliest evolutionary steps that has already been erased by Earth. So we don't have a way of looking back in the past that far. Living chemistry of Mars would allow us to have access, potentially, to information that would help us understand how chemistry became biology, which is one of the very biggest questions. And finally, if we're really talking about the future of life on Mars, the most exciting, maybe even unsettling question is if Mars hosted life for a long period of time, is it still there? We know that Mars has heat inside of it still. Like the most recent volcanic eruption on Mars was not billions of years ago. It was millions or even maybe less than that of years ago. So we know there's still heat in there. We know that there was once water. We know that we are pretty sure that there is still subsurface water. If that subsurface water is near something warm and there was once life on Mars, then that life, it seems entirely possible, especially given what we know about sort of deep down life on Earth, that there would still be living microbes in, if not on, Mars. And that would allow us to observe it directly which would be, I don't know, like that would, oh God, that would be so cool and good. But also, we'd have to make sure that we don't kill it. That would suck. If we killed the life on Mars, it's one thing to extinct a species. It'd be another thing to extinct a biosphere by introducing all of our advanced stuff that's had a bunch of time to thrive and evolve. Like ultimate invasive species, right? Like moving into Mars and be like, oh, whole planet to go after, give me it. I'm talking about microbes being the invasive species here, not humans, though ultimate invasive species right here. We can invade anywhere. We're in Antarctica. We went to the moon. So yeah, isotopic fingerprints of carbon-based chemistry, lipid backbones maybe locked up in the clay, maybe even, I didn't talk about this, microfossil like type stuff like the Allen Hills meteorite. That's how you sort of build the picture, like one, that there was life, and two, what was that life like? The questions don't stop coming. This is one of those big questions that becomes a trillion questions once it gets answered. If it gets answered in the positive, this one question becomes a trillion questions, and like a trillion very exciting questions. But I think it's important to say that the way that this is happening is reflective of almost every big scientific claim turning into consensus. So you get the early hint, you get contradictory data, you get tantalizing maybes, you get years of debate, and then you finally settle that debate. My favorite example of this is like, when were atoms discovered? Like, was it when Democritus said, I think there are atoms, and I'm gonna have a philosophical debate about that? Was it when Dalton and Lavoisier were like, look, we're doing all this chemistry, and it's all happening in whole number increments, and that seems weird. So probably stuff exists in discrete units, like atoms. But maybe it wasn't then. Maybe it was when Einstein was like, I did the math, and Brownian motion only makes sense if things are made up of physical particles. Or was it when Max von Laue did the first X-ray crystal diffraction images, and it was like, look, this doesn't make sense unless they're like balls in there. Science doesn't usually end up with like the Viking lander lands and then it looks out and it's like, hey everybody, look, moss. It's usually like drip, 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 and then eventually the flood is big enough that everybody's like, yeah, that room's wet. Is that a good analogy? It'd be great if one day an alien landed and was like, hello, you're not alone. Take me to your YouTuber. Bring them to me. I want to talk. Usually it's not like that. And so these things that are huge, can feel, when they finally happen, pretty anticlimactic, because there's the debate has been going on for so long that it doesn't happen in one moment. It's just like consensus slowly builds until everybody's like, yeah, put it in the textbook. So like possible biosignature strengthens evidence for habitability. It doesn't sound like the stuff of the front page headlines, but usually like extraordinary achievement doesn't happen all at once because it needs a bunch of evidence and a bunch of interrogation. It needs to make its data available for other scientists to challenge. That challenging takes a bunch of time. If like a good challenge comes along, you have to figure out how to answer that challenge, or you have to realize that you can't answer it, or you have to accept that probably you were wrong. The body of scientific knowledge is the stuff that has survived contact with intense skepticism. And that takes time. And it makes me realize that like, if we find life outside of Earth in my life, which is totally possible, it'll not be that big of a news story, which is kind of hard for me. Like, in a very real way, it would be the biggest story ever. But because it's probably going to be more of a slow tipping of the scales toward, that seems like the most likely explanation, it probably won't be that big of a story. Just like you may very well have gone through this week, though admittedly, and for good reason, there was competition for that news space. But like, you may have gone through this without knowing one of the most important discoveries in the history of planetary geology. And like that the scale is starting to get tipped in the direction of like, there was once life on Mars. Now, I'm not saying that it couldn't tip back the other way, but like, it's starting, as a person who like cares about this and has looked at it for a long time, it feels like it's going one way now. Many times in the past, Mars has raised our hopes, and skepticism and evidence have cut those hopes down a little bit. And I will be honest, I want there to be life on Mars. So just like, that bias is there. But every time we get that dynamic of like new evidence and then like, ooh, well, what about this? We inch forward toward the truth. And if we do answer that question that has been in our minds since we figured out that there were other planets, that question, once we can use the laboratories of Earth, might be fairly easily answered. Now, getting the vials home to Earth, that's not going to be easy. But once they're here, we know how to do the analysis. In conclusion, John, everything we know we figured out. This is a very big question. It's one of the biggest questions. But we are always, as humans, but it feels like especially now, in a time where there are a lot of big questions that are unanswerable. Not like, I don't know how we'll answer that, or I don't, like, when will we get to the answer? It might be a long time, but like, just unanswerable. Because humanity, groups, individuals, the whole thing, it's just too big and complex. And I'm feeling that a lot right now. But in this case, there's like a really big question, and there is a potential path to certainty about a big question, and then moving to the next set of questions. And that, I think, understandably, I find comforting. John, I'll see you on Tuesday.